Okay, we're live. Well, I don't have Sahil to check it for me. Just wait a little bit.
You can just wing it.
Yeah. Well, if the audience hears any echo, please let us know. I will try to fix it. But let's wait a few seconds. Alrighty. Hello, everyone. Welcome to today's episode of Quorecast. I am your host, Tim.
Now, Mikey.
All right. So, unfortunately, today, Sahil is not with us. So, we'll try our best to do Sahil's part. Before we begin, today's episode is going to be about supersymmetry, and this is a continuation of last week's episode. So, Mikey, why don't you try to recap a little bit on what we did last week?
Okay, sure. I would like to recap a little bit before that too. So, the episodes before that, we discussed symmetry, right?
Mm-hmm.
And I think that the point that I want to stress is that um, in order to understand anything in the universe, you have to be able to say whether or not these two things are similar to each other or these things are dissimilar to each other. Um, in other words, we need to draw relationships between the objects in our universe, and that's essentially what symmetry is. It's a fancy sounding word, and it might not seem like relevant to understanding, but when we talk about a symmetry existing in nature, what we're really saying is that there's a relationship between these two things. Um, and that is really the crux of what allows us to understand the universe, understanding that two things can be similar or
Mm-hmm.
dissimilar. So when we try to write down laws of physics, we look for symmetries, we look for relationships between objects, whether they seem related or whether they don't seem related. And that's essentially what theoretical physics is. It's establishing
Right.
these relationships. And yeah,
So we talk about
supersymmetry is probably the most, yeah.
yeah. So we talk about supersymmetry, right? So what's special about supersymmetry?
What's special about supersymmetry? Okay, I'm just gonna wing it. What's special about supersymmetry is that um, it's kind of like an exception to the rule, right? Like we know that space and time have a relationship. They're not independent objects. There's some relationship between space and time, and we understand this as what we call a space-time symmetry. And this allows us to understand phenomenon like special relativity, like time dilation, like contraction, um, how space and time can kind of like uh, rotate into each other, so to speak. Um, and for the longest time, uh, there was a theorem that said that the relationship between time and space is the only relationship that you can have between space and time. But it turns out that there's a loophole to this argument. Um, oh gosh, this is about to get technical. um,
Well, I guess we did go through that a little bit yesterday. Last week, we're going to delve into a little more details now. There's this concept of superspace where one can actually generalize space-time, and space-time have these extra directions where you can hop into, and that's actually the better way to think about supersymmetry. But I want to focus on, just to get our audience acquainted to what we're going to talk about. Today's topic is about bringing balance to our universe. So
yes.
so how so first of all, why does balance matter, and why supersymmetry? Maybe like a this might be difficult, but like a one sentence summary what this is going to be about.
Wait for me.
I'll give it a shot.
So the universe needs balance. The universe the universe appears to be a chaotic place where chaotic things can happen, right? Where violent things can
Mm,
happen. But we know that the universe that we live in is pleasant. It's not like a violent, chaotic mess. We know that space time is smooth. We know that the energy density of the universe is low enough that we can exist in a pleasant um, environment. And these are things that we take for granted. But if you look at the laws of physics kind of paint the picture of a universe that wants to be violent. It wants to be imbalanced. It's like it's you can kind of imagine it as like um, I don't know, like a chopstick hanging on like on a pivot or something. Um, and it turns out that the only way to bring balance to the universe that we know of is supersymmetry. The only way to bring peace to this violent, chaotic tendencies of quantum physics is, you know, and it's a classic story of yin and yang, right? Like you have two opposing forces, and these two opposing forces need to balance each other in order for us to have a peaceful existence. You can't have one heavily outweighing the other. This leads to chaos and violence.
So I guess it's worth to dig a little deeper, right? I think in many episodes before we have talked about why the world is so chaotic and so seemingly inhospitable. Where does that come from, originate from, really, in physics?
It comes from, well, quantum fluctuations, right? Like, I guess you could say that it's kind of a rule in physics that anything that can happen will happen, right? And if extreme violence can happen, then it will happen unless there's some constraint that forces it to be non-violent. And probably the biggest source of violence in the universe comes from these two opposing forces. When we look at particles, we notice that there's two different kinds of particles. There's what we call bosons, which we mentioned before, which, you know, stack up on each other and sort of like want to make the universe compress. And then we have fermions, which make up our bodies, which sort of oppose this compressive force and, you know, creates spatial extent in our existence. And yeah, this is really where we're at right now. These are the two opposing forces that supersymmetry draws a relationship between and creates tranquility.
Yeah, maybe we should be a little more specific. I know we're talking about forces, but I think you may be more specifically talk about the cosmological constant, which is a force of gravity, correct? Is that what you're referring to? Yeah.
Yeah. Well, no, not really. I'm referring to just, you know, even disregarding the cosmological constant, right? The universe just, quantum physics wants to be violent. Quantum physics is a violent theory, and it needs something to control it. Otherwise, we can't explain our existence.
I guess that's fair. I guess every force, whether it be electromagnetic, strong forces, or the weak force, in the presence of that force, particles, pairs can get created and destroyed. And that is usually viewed as the source of quantum corrections or quantum fluctuations, right?
Should we go through this exercise of seeing what happens when we try to look at things on smaller and smaller distances and how violent that can get?
Yeah, I think we should we can recap that really quickly, I think.
Yeah. Would you agree that comes from the uncertainty principle?
Yeah, I think that's fair. I think the uncertainty principle usually at college physics it's just about one particle having energy. They could have different amounts of energy, right? And even though something might seem to be exactly at rest, in ordinary physics, in quantum physics, they could jiggle. But if you take into Einstein's idea that E equals mc squared, if a particle can get enough energy to jiggle in particle physics, there could also be enough energy to procreate more particles, right? So that's why particles can come and proliferate. And we can see that in vacuum. I think in the previous episode, you and Sahil talk about the cosmological constant problem. Why don't we go over that explanation briefly?
Wait, do we have to tie this to the cosmological constant? Because really what we're talking about is the fact that, like, the more closely you look at something, the more violent its behavior is. And that's just a fundamental fact of quantum mechanics.
Right. But cosmological constant is just one example, right? I would agree with you.
The ultimate example, yeah.
It is the ultimate example because with, you know, if the cosmological constant is totally out of whack, then there is no balance. There's no universe to even have forces.
Wait, we didn't explain what the cosmological constant is.
Yeah. Okay. Well, I know we went through that in the previous episode, right? So in nature, we have different forces. Probably one can argue that the greatest force is the force of gravity, right? And Einstein says gravity is generated by the existence of other stuff. Anything that has energy or mass can gravitate, right? One interesting fact about gravity is that gravity is always attractive, although we'll come back to that later. With one exception. It turns out that gravity itself can gravitate. So just the existence of space-time itself, it can cause things to gravitate. And this gravitation can actually be positive or negative. And Einstein famously called this the biggest blunder of his work, which turned out ironically to be true. That so this is where cosmological constant comes in. If you have a positive cosmological constant, I think my signs might be wrong, but bear with me. If you have a positive cosmological constant, it means that gravity, when you have some gravity, it will tend to create more gravity. More stuff begets more stuff. So this will cause the accelerated expansion of the universe. Space creates more space. If you have a negative cosmological constant, space will kind of collapse upon itself. So space will create less space. It's almost like, I don't know, it's almost like an interest rate, right? Like you can compound interest your money, or if your currency is degrading, you can compound negative interest, and you know the value can get inflated away.
Yeah, so if you're screwed, you get more screwed.
basically. But I think it's fair to say that in physics, there's no reason why the cosmological constant has to be exactly zero, right? There's no reason, I think.
Wait, do we have to use the word cosmological constant? Why can't we just use the word vacuum energy, like the energy of empty space? That's really what we're talking about.
Yeah, that's exactly what we're talking about, right?
So that's really the question. The idea of this cosmological constant is if I just take a empty box, like a box, and I take all the stuff out of it, and it's just completely empty, how much energy is in that box? Quantum mechanics says that it's not zero. There's some activity because of the uncertainty principle.
Right.
And so if I take a box and I empty it of every single, like it's completely empty, just nothing's in it, that box will still have some energy in it. And the question is, how much energy is in that box, this completely empty box? But that is the question. Yeah.
But it could be positive or negative. I think that's the point.
Yeah,
but not zero.
The box could have positive or negative energy. Why would it be exactly zero? It has to be exactly zero, almost exactly zero, in order for us to enjoy a pleasant existence. Because if an empty box had an intense amount of energy, then obviously it would be very difficult to live in such a box.
I think it's fair to say that we have measured this value. In fact, we can just see it, right? Like the fact that this box in front of us, I know there's air in front of me, but if you extract out the air, the box of space in front of me doesn't just instantaneously implode or instantaneously collapse. That's an experiment we do every day at home, right? So it tells us that the vacuum energy is very small, very, very close to zero. But actually, it turns out that it's not exactly zero, right? We measure that. So, is it fair to say that this is one of the biggest conundrum in theoretical physics?
Oh, it is absolutely the biggest conundrum in theoretical physics. Why is space smooth? Why can my hand pass through space? If there was an intense wall of energy here, then my hand would not be able to pass through without getting burned.
Right.
Well, it can. And that turns out to be kind of a mystery because the fundamental laws of physics say that empty space can be an extremely violent place.
So let's bring it back to supersymmetry a little bit, right? So we mentioned this concept of balance. So okay, we have this vacuum energy, and we ideally want the balance between positive vacuum energy and negative vacuum energy. We want them to balance out. So where does supersymmetry come in?
How can it be that the energy contained in an empty box can be so close to zero when anything that's possible, anything that can happen will happen? That is the crux of the dilemma, I would say.
Yeah. I think in high-energy physics, people have found all sorts of loophole to try to balance it out. There are all kinds of theory that says maybe some things contribute positively, some things contribute negatively. Maybe there's universes that have positive cosmological constant, and then universes with negative cosmological constant. They kind of balance each other. But I think it's fair to say that in all these theories, you gotta give and take. There's got to be something on the positive side, kind of weighing against the negative side, right? I think that's
Yeah.
fair.
Yeah. In order to have a peaceful, tranquil universe, you have to, there's violent forces at work in the universe. And in order to live in a tranquil, peaceful universe, there needs to be balance between positive and negative.
So I guess this is where the story becomes interesting. And it turns out that there could be a balance if you separate particles into two groups, bosons and fermions. So what's the best way to explain this balance?
That's tricky, I guess. So as we discussed, there's, we really like to, I mean, it's not that we like to, it's we're forced to really view the universe in terms of two types of particles. There's the particles that give rise to stuff like the table and the chair. And these particles are made of fermions. And fermions, in a sense, they repel each other and they create spatial extent. And then we have force particles like particles of light, which can pass through each other, can occupy the same space at the same time. And these two types of particles turns out plays a fundamental role in this balance of the universe.
So
What
is
am I
it
trying to get
fair?
at?
Yeah, I think it's fair to say this analogy might not be perfect, but I think if you view if you view the vacuum as popping particles in and out, right? If you if let's say some bosons get popped out, like particles of light, particles of forces, or gravitons pop out, because of gravity, they're gonna attract each other, and because they're
Oh,
bosons, they like to kind of clump together, and that causes space time to have a tendency to collapse a little bit. And I think that contributes negatively to cosmological constant. Although I could be wrong with the sign. There might be some
no, I
convention
think you're
issue.
right.
Yeah. But fermions, on the other hand, they kind of have a tendency to not do that. And they repel each other, kind of. And we see that in stars, right? Because in the sun, there's intense gravity trying to collapse the sun. But there are electrons and protons. And the fact that the electrons are so stacked on top of each other, meaning that the sun maintains its shape. It keeps burning. So this property of fermions to kind of keep their ground, basically. They don't let each other walk all over their friends, right? They stand their ground. And that causes space time to kind of hold itself up a little bit. And that causes positive, it's a positive contribution to cosmological constant. And it turns out that physicists, I think back in the days, discovered that you could actually make this balance exact between fermions and boson. Their collapsing tendency and their resisting tendency. Yeah, pushing out, resisting out tendencies could perfectly cancel each other out. And that's but I don't know if historically that was the way supersymmetry was discovered, was it?
No, it wasn't. No, yeah, that was an afterthought.
Right. So it turns out that for the vacuum energy story, that is correct. But I think that's just one example of what supersymmetry does. Sure, it's a symmetry, it's a relationship, it's a pairing between bosons and fermions. But these properties, right? It's a consequence of that. But Mikey, could you? I think you have more knowledge about the historical context on how supersymmetry was discovered in the beginning. Could you give us more details?
Um, yeah, I mean, as far as I know, conceived as a necessary ingredient for string theory, and it was only after the fact that it was realized that it has these amazing properties that it can bring balance to the universe by canceling positive and negative forces. The universe's tendency to want to collapse and the universe's tendency to want to, have some spatial extent. And
I think the story for string theory is similar, right? Because initially, if you only have what they call bosonic string theory, meaning that if strings were only made of, if strings are only made of things that are similar to particles of light, the universe will have tendency to collapse, and that's one of the problem. That's why string theory is unstable, right? Because it's a negative vacuum energy. And lo and behold, once they add supersymmetry in it, they're like, hey, look, these two pieces kind of keep them in check. And then lo and behold, string theory becomes consistent, which is magical, basically, I think.
Yeah, I would agree with that. So how are we going to address the haters?
Huh?
How are we going to address the haters of supersymmetry? I feel like that's really what this is about, right?
Yeah. So I think at face value, this postulate. So historically, supersymmetry was first conceived to solve some of the issues with string theories, and people were kind of naturally curious, be like, hey, like it make the theory make sense. But then slowly but surely, they discover other more amazing properties, which we're going to go through later on. So theoretically, it's a very sound idea. It's an amazing mathematical tool. But then after a while, I think people start to think that, hey, maybe this has to do with real world, right?
Mm-hmm.
And then there's this concept of what we call, I guess, physicists usually call it the weak scale supersymmetry. It means that supersymmetry relevant for the real world. But unfortunately, many of the predictions of supersymmetry does not hold true. But I don't think that's a fair criticism for supersymmetry, though.
Yeah, I don't think so either.
Yeah, but perhaps we'll go through that later. I think we should first address one of the audience question, and it's also one of the things that I added to the cover page of this episode. Is this equation that Q equals 2 sigma P? Roughly speaking, Q times Q is P. So what exactly does that mean, Mikey? Can you break that down for us a little bit?
So we went over this a little bit in the last episode that, supersymmetry is basically the idea that space-time is bigger than we thought it was, that there's an extra direction that you can walk in space. And this is not a typical kind of dimension. It's not the kind of dimension that you can walk through continuously, but it's a discrete dimension that it's like you can flip to the supersymmetric side of the dimension, and you can flip back. And cute, what we and
yeah, I think Q literally means a walk. You walk in this direction once, and then Q bar, it means that you walk kind of again. And then P means that you will get a spatial movement. So P here could mean a walk to the front, back, left, right, up, down, or in the time direction. P actually has full possibility because Einstein, as we know, it's not just space or time, it's space and time, right? But then the Q, these super dimension, also has 4 possibilities. These are a little more abstract, I think. It has to do with spin, so you can kind of loosely imagine us like spinning one way versus there are 4 different ways of spinning. If you spin in one way and then spin back the other way, you somehow get a movement in ordinary space. But isn't this equation just so ridiculous? I think it's ridiculous, right? Like these, and I love this equation because on the left-hand side, it's spin. It has nothing to do with moving in space-time. On the right side, you move in space-time. It's like, holy crap.
Is it more ridiculous though than special relativity though, where you imagine that like time and space are related to each other?
Oh, I mean, of course, when it first came out, people were it was so profound when Einstein first came out with this idea. Somehow somehow you can slow down your rate of movement in space or time, right? Like length contracts, space, time dilates. That's crazy. But of course, now we got used to it. But then Susie, I think it's like the next step. It's like, hey, dude,
Yeah. The
if you
natural
spin,
extension.
yeah, if you spin in this fermion direction, you can take a walk in space time, and that's just insane.
Yeah. Well, I mean, I think the most insane thing about it is the fact that you can mathematically show that this is the only possible way to enlarge the space-time symmetry.
Yeah. Okay. I think we should talk about that a little bit. So you mentioned this is I think the famous Coleman-Mandula theorem, right?
I've
Um,
tried so many times to try to understand. Yeah,
yeah,
it's just mathematical.
it's very mathematical. Basically, people were back in the days they were trying all kinds of symmetry basically.
Yeah,
They
what
were
are
they
all the different kinds of relationships that you can have in space and time between objects?
yeah,
People
and
people try to enumerate them and count them.
I think initially people tried to come up with new symmetries that makes Einstein's symmetry bigger, right? But then
Well,
they
we
couldn't
need
do it.
symmetry. Yeah.
They couldn't do it. They couldn't do it, right? And then lo and behold, Sidney Coleman and who's Mandula? I forgot. I should know this. Um, but two great physicists, they proved this theorem and says that, hey guys, stop trying. It can't work. They proved that the only ordinary symmetry that is consistent with physics, meaning that, hey, you can't go into the past to kill your grandpa. Particles have to make sense. You can't just have particle appear here and we appear in Andromeda. So some very basic property, consistency, right? Probability has to sum to 1. If you assume that, then Einstein's symmetry, the Lorentz symmetry, space and time, it's the only possible symmetry. And afterward, people kind of gave up. They're like, wow, shoot. Einstein was right. It's the only possibility. They gave up, I think.
Yeah, it's called a no-go theorem.
Yeah, it's a no-go theorem. But then it turns out there's a loophole, right? And the loophole has to do with the fact that supersymmetry is super. I think it's fair to. I think it's fair to say that it's not. I think technically it's not exactly a symmetry, but it's a symmetry. Yeah, because it's not like exactly you. Symmetry is like usually you rotate around, you flip an object, you move left and right? But supersymmetry is weird, and I think it comes down to this extra negative sign. There's this fermion. There's this the technical word is that it anti-commutes. There's an extra sign, right? There's an extra negative sign, but I'm not sure how to explain that. But anyway. If you flip one sign, it turns out there's this loophole. But then I think that the theorem got expanded. I think it's true that the only consistent symmetry is Einstein's relativity extended to basically the super symmetrized version of it, and that's it. I think. Is that true? I think that's true, right?
Yeah, that is the content of the Coleman-Mandela theorem. Okay, but so suppose I wanted to play devil's advocate, and I was like, okay, like, why is supersymmetry the only symmetry that can give balance to the universe? How would you answer that?
I mean, part of it is that it's the only one we came up with.
No, it's theoretically. I mean, you can mathematically.
Yeah, I think you.
Have any, how does it work? Like, if there were any more symmetries, then it would essentially be random. That's the contents of the Coleman-Mandela theorem, right? That if you allow any more symmetries in space-time, then anything can turn into anything.
Yeah, I think roughly that's how the proof goes. If you allow an additional symmetry, it means that you screw up some of the calculation. There's some craziness that gets injected into the theory. Like you might break unitarity, meaning that
momentum wouldn't even be conserved, right?
I think there are multiple angles.
You can show that like two particles going in can go out at any angle. It doesn't have to conserve momentum if you assume anything more.
Well, yeah, you get a contradiction, I think, but I don't know the details. But anyhow, let's get back to the topic, right? So So supersymmetry is the unique idea that allows cancellation between things like the vacuum energy and other things. But can we talk about why is this cancellation important? Why should we have this cancellation? I know we mentioned some of that.
No, I mean, yeah, it's because we have to live in a peaceful, tranquil space because this is what we observe.
But I think it goes beyond that, right? Because we mentioned that in quantum physics, when an interaction happens, everything else goes along for the ride. So if we collide, let's say, particles of light, that particles of light can emit a graviton, and that graviton can do all the violent things without supersymmetry, and that will destroy the properties of the photon itself. And this goes into theories of, there's many technical terms, I don't want to get into the details, but quantum corrections basically will leak into everywhere. It will corrupt almost everything imaginable.
We're just talking about the universe's tendency to want to be violent.
Basically, yeah. So universe very much wants to be violent, but Susie is kind of like the savior. But let's talk about practically what happens when physicists discover this cancellation. I think a lot of theoretical physicists rejoiced because once they see all these ugly equations, like imagine you do pages and pages of calculation, it's like this is hopeless. 5 pages of calculations. Oh my god, like I compute 1,000 terms only to, it's completely intractable. But then they discovered this kind of cancellation. It simplified a lot of calculation, yeah?
Yeah, but how do you know that's just not an artifact of our ignorance?
Well, I think that's the belief, right? So with the supersymmetry, I think it enabled physicists to do some heroic calculations. Like I would say you couldn't even do calculations in string theory previously, like any serious calculation anyway, or even calculation in quantum field theory, just like even if you shoot some particles at each other, like photons and electrons, what's going to happen? You can only approximately get it, right? Yeah. But what's amazing is that with supersymmetry, you get exact answers. And that's crazy.
Yeah, but that doesn't mean it's correct, right? That just means that it's convenient for us.
Well, of course. But with that, I think it's fair to say that physicists discover a whole new host of relationship called dualities. I think we shouldn't undersell supersymmetry in that, and that's
yeah. I mean that's definitely one of the most amazing byproducts of it, but I don't know. It makes it seem like it's just a convenience for us, right? As people trying to do calculations. Oh, this makes calculations easier. So, but that's not really what it is, right?
Yeah, that's not really what it is. And I think one of the example is this concept of duality. I want to just clarify this concept of duality. So what is duality? Duality is this idea that one physical phenomenon can be described by 2 different language, right?
Yeah.
It also means that if you have 2 different theories, because theories are really just language for us to describe things, even though the theories might look totally different, the equation is totally different, the underlying physics might be exactly the same, right? That's what they discover. So basically, supersymmetry allows them to unify 2 phenomena that people thought were different, turn out to be the same. So one of the example, I think this is true. Mikey, correct me if I'm wrong. There's actually a famous duality in electromagnetism, where if you study the equations of electricity and magnetism, you can actually flip the equations for electricity and magnetism. You imagine electric field becomes magnetic field becomes electric field. You can flip them, but so they would look approximately the same, but it's not exact, right? But supersymmetry fixed that. I think that's fair to say, right?
Does it? Does it create electromagnetic duality?
Yeah, so I think this is it called S-duality? So physicists have come up with theories where this duality is exact. I think that's fair.
Why is that important? I don't get it.
Well, I think it's a hint. It's a hint that saying that if your theory doesn't have supersymmetry, it's ugly.
Yeah, but I would argue that supersymmetry is the only way to balance the universe. It's the only way to create a stable vacuum. Like how can you do so otherwise?
Yeah, I think that's fair. And even so, so I know there's a lot of naysayer that says, "Hey, we don't have no evidence of supersymmetry." But even if we don't discover supersymmetry, um, at very very high energy, there is no other mechanism to stabilize spacetime. I think,
Yeah.
right?
Yeah.
Yeah.
We're not
So
being convincing though. We're not being convincing. Like, sure, there's mathematical theorems that prove this, but you know,
okay. Yeah, I know. I know we're coming short on time. What should we talk about? Should we cover some of the briefly summarize some of the issues with supersymmetry?
no, I don't think. I mean, the issues of supersymmetry are, I feel like they're cheap shots. Um, it's like when someone tries to make a point and you find a counter argument that isn't really relevant.
Yeah.
I
Well,
think I
well
think
let,
I think we should finish on trying to establish why. Okay. So what are the final thoughts on why the universe has to be supersymmetric?
yeah. I mean,
If you assume that the universe is not supersymmetric, then you're saying that these two opposing forces, these yin and yangs that we've been talking about, have absolutely nothing to do with each other, um, and there's no relationship between them. Um,
yeah. I think at the end it's really just like Star Wars vibes, right? I mean, you imagine it's just like Yoda teaching us the ways of the force of the universe, and and part of that, of course, is philosophy. Um, people will say that hey, there's no evidence for supersymmetry, but let me correct that. When people say there is no evidence for supersymmetry, sure, partly they're correct, but they're also referring to a one specific version of supersymmetry, the weak scale supersymmetry, right? There's no evidence for it, and you can argue that maybe the evidence is against it, right? But supersymmetry in general, we don't know. Of course, you can say, well, if we don't know, should we just say no, right? But for now,
what I want to know is for the naysayers, do they not believe that the universe needs balance? Like when people say that there's no evidence for supersymmetry or whatever, do they not think that
yeah,
quantum
I,
mechanics is implies that the universe should be a violent place and there needs to be something to cancel it out?
I would say it comes from a place of negative arguments. It's
Hmm.
not that they don't believe there needs to be balance, it's because people don't care. Because it's not an immediate theoretical problem, you know?
Yeah.
Yeah, so it's like, hey, we see that there is balance in the universe. The vacuum energy isn't really large or really
The
negative.
universe is pleasant.
And you can take the perspective that I just don't care. The universe is just what it is, right?
Yeah.
But
Yeah.
then if you do care, you have to say, well, there's got to be balance in the universe. And now if you say it's not supersymmetry, you can either resort to a negative argument to say, hey, well, I don't like supersymmetry. But then if you take the perspective that hey, science needs to be positive, that means that if you say something is bad, well, propose something better. But the problem is
Yeah. The
there is
naysayers never have better alternatives,
the
but
problem is there is none. So, but okay, so I guess we're way over time, but we should summarize, right? So Mikey, what are your thoughts on this? On this?
okay. So my thought on this is that like space is smooth. We need an explanation for why space is smooth, for why the universe is a peaceful, tranquil place. There are these two opposing forces that clearly um, clearly create violence in the universe if they're not balanced. And there's a mathematical theorem that shows that the only way to bring balance to the universe is to assume that there's some relationship between these two opposing forces. Um, and for me, that's enough. Like, I'm sold.
Yeah, and I guess I know Mikey, you and I we are cut from the same academic cloth, so so partly, of course, I agree with that. I also want to highlight kind of the historical lesson. Like when Einstein first came up with this idea, space and time are related, people thought he was crazy, right? He's like, oh, there's no way. There's no way space can shrink, time will expand, whatever, depending on how fast you're moving. That's just nonsense, right? But it turned out that Einstein was right. And in fact, the experimental verification for Einstein's theory came much later. His insight was so brilliant and his vision for how the universe was so beautiful that people can't help but be compelled to believe in it. You know? And I think supersymmetry, and a lot of physicists do buy into it. And I bet you, if students spend some time learning on it, probably everyone I've met will be like, oh man, this is like, the structure is just so amazing. Like, how can it not be right? And in fact, it's the only way to unify space and time and the different types of particles. And it's like, maybe like Einstein's story, the verification will be delayed hundreds of years, multiple lifetimes. We'll never figure it out. But it's this conviction to believe that something this beautiful it's gotta be something. And so a lot of physicists just kind of, sure, we don't have experimental verification, but a lot of people I think decided to keep going to see what supersymmetry can bring. And the more they learn, the more they discover, right? Yeah. It's almost, I think supersymmetry is one of those things that it clearly seems like something we found instead of something we invented.
Yeah. I mean, one thing's for sure, the only people that hate on supersymmetry are the people that have never studied it.
Yeah, like I'm not saying that supersymmetry is correct.
I'm saying it is correct.
But well, I would say that a good part of it almost definitely will be correct. Like
if you say that supersymmetry is not correct, what you're saying is that these two types of particles, this yin and the yang, there's no relationship between them. It's just completely two completely independent things.
Well, let me put it differently. What I'm saying is that supersymmetry may not get the whole picture right, but it's definitely part of the picture.
Yes, it's definitely part of the picture. Yeah,
it's definitely part of the picture.
There's definitely a relationship between yin and yang. Otherwise, how can we exist?
Yeah. Well, and I also want to add that with these fantastical terms, this is kind of like the closest we'll ever get to Star Wars references, right? Like the yin and yang, the good and not exactly good and evil, but the bosons and the fermions, and this is how physics brings balance to the universe.
So which ones are good and which ones are evil? The bosons or the fermions?
I
think the bosons are evil.
You think?
Yeah.
Well, the fermions do tend to create instability. I don't know. They could be evil too, but then they stand their ground. So I don't know if I'll agree with you that bosons are the bad guys, but let's just agree that they need to exist in balance one way or another.
There needs to be a relationship between these two opposing forces. If there was not a relationship between them, there's no way that space could be a tranquil, smooth place to live in.
All right, I think we're at time.
Okay.
Yeah. On that note, I want to thank everyone for joining us, and see you all next week.
Yeah.
Bye-bye.
Bye. Damn, that was